This is chapter 9.5, exercises 23 through 30, and this is the section that deals with series, which is the summation of sequences, and we have a small problem set. 23, find the first 6 partial sums of the following infinite series. The sums have a finite limit, write convergent, if not, write divergent. So we have really a part A and a part B. Well, in this case, we're going to write part A below. I'm going to go down to give myself a little bit of room. So to write the first 6 partial sums, well, we just add these consecutively. So the first partial sum of this series is going to be 0.3 because that's just adding the first to itself, and the next partial sum is going to be these first 2 added together. Okay, so we have 0.3 plus 0.03, and add together these are going to be 0.33. So that's our second partial sum, and as we proceed, we have a pattern. The next one is going to be just the same as the second partial sum, but adding on the 0.003. So the next partial sum we put down is 0.333. The next one is going to be to the 10,000th place, so 0.3333. That's our fourth partial sum. Our fifth partial sum is going to be 0.33333, and that's to the 10,000th place. And the last one, our sixth partial sum, is going to be 0.33333, and that's going to be to the millionth place. 333,333 millionths. All right, and then as far as convergent, divergent, okay, well, this series here is going to be convergent because this thing, if you might recognize this from a calculator, what does this converge to? Well, this is the decimalized version really of 1/3, so we're converging to 1/3 as we go on. Let's go on to part B. Okay, we're going to do our partial sums. We have 1 is our first partial sum, and the second partial sum is to 1. We subtract 2, or we could say add -2. So 1 minus 2 is going to be -1. So that's our second partial sum. Our next partial sum is we take this -1 and add to it 3, and -1 plus 3 is going to be 2. That's our third partial sum. And then 2 minus 4, the next partial sum is going to be -2. Our next partial sum is to -2, we add 5, which we're going to, when we do, we're going to get 3. And our sixth partial sum is going to be this value, 3 minus 6, which is going to be -3. And so you can see a pattern, don't you? You have 1, -1, 2, -2, 3, -3. The next one is probably going to be 4, -4, or next 2 anyway. And so what does this series do? Well, this series, what this does, it diverges. So we call this a divergent series. The series does not hone in on one value like part A did. So let's go on to our next other problem, which is problem 25. In exercise 25 to 30, determine whether infinite geometric series converges. If it does, find its sum. Well, what I'm going to do now is introduce the formula for finding an infinite series, the convergence of an infinite series. First thing we need to do is figure out whether the series converges. And if we look at the numbers getting progressively and systematically smaller, which we do, we have, if we to go from 6 to 3, well, that would be subtracting 3 or plus negative 3. But really what we're doing is our common ratio is going to be a sub n over a sub n minus 1. So if we take 3, which we call a sub n minus 1 is 6. 3 over 6 simplifies to 1/2. So this is going to be our common ratio. And to find the sum of an infinite series, which I'm going to write in sigma notation, if we say from k equals 0 to infinity of some relation, we call it a function or something like this. We'll call this a sub k, I don't know. But that's going to be simply your first value, a sub 1 over 1 minus r. That's it. Now, in the previous videos, we've noticed the summation of a non-infinite geometric series, which is a sub 1 times quantity 1 minus r to the power of n over 1 minus r. Well, what's happened is that this 1 minus r to the n is just simply replaced by a sub 1. And what happens is, as we go toward infinity, what does 1 minus r to the n become if we're a convergent series? This approaches 1. Okay, so approaches 1 as we approach infinity. And so we're left with a sub 1, and the book calls it a over 1 minus r. I like to call it a sub 1 because that's our first term. In this case, we have, let's go ahead and apply the formula. We have, is this series convergent? Yes. Converges. We'll say, determine whether, I'll say yes, comma, converges. And if it does, find its sum. Well, we're going to apply this formula. We're going to say that the summation is going to be a sub 1 over 1 minus r. In this case, our first term is 6, and 1 minus, well, 1/2 is our r, and so that's going to be equal to 6 over 1/2. And going back to 7th grade math, if we divide by a fraction, it's the same as multiplying by the reciprocal of the fraction, so 6 divided by 1/2 is the same as, I mean, 6 times 2 over 1, right? 1/2, 2 over 1, the reciprocal of 1/2, which is going to be equal to 12. And if we put this in, I want to show one more thing in the calculator. We can also enter these in the calculator. And to do that, if we put, let's go ahead and put this notation here. We say k equals 0, and we're going up toward infinity, and we have a sub 1, which is going to be 6 times 1/2 to the power of k, and we go toward infinity. What happens is our calculator is not going to be able to recognize infinity. If you put infinity in, at some point, the calculator does not recognize infinity as a number that it can calculate with. So what you have to do when putting this in the calculator is put a number in there. Now this series is going to go down toward 12 pretty quickly, and so what we can do is put a number in there for infinity in its place, and we go next to the 9, and we come here to enter, and we're going to start out with k equals 0. Instead of putting infinity up here, we can put a number the calculator can deal with. Typically, I've seen that be 100. Also, 50 gets you pretty close. And what do we have here? We have 6, which is our initial value, and that's going to be times. And let's get it. We have 1/2. And what do we raise that to the power of? We raise that to the power of k. And so here we have it. Let's see what we get. So we get this improper fraction. We're going to decimalize by pressing Control, Enter, and the thing rounds off to 12 in the calculator. Now, it's not exactly 12 at 100 because it's only infinity that will get this number exactly to 12, but the calculator, given 100 instances there, recognizes this as the value 12. So that's the way you can do this in the calculator with the with the sigma notation feature. All right, next, let's go on to next on our problem. We have determine whether the infinite geometric series converges. If it does, find its sum. Now we have fractions, and fractions is a hopeful thing because we go to fractions. That tells us sometimes that we're going to be able to perhaps converge to a number. Well, let's look at this. We go as we proceed from one value to the next. Okay, A, remember R, our common ratio is A sub n over A sub n minus 1. In this instance, if we take 1/32, which is going to be, we call A sub n, divided by its predecessor term, which is 1/64, to divide 1/32 by 1/64 is the same as taking that 1/32 times the reciprocal of 1/64, which is going to be 64 over 1, and so that's going to be 2. And so what we have is R equals 2. Well, for R equals 2, we need an R value of less than the absolute value of 1, or the absolute value of which is less than 1 to converge. So, does this series converge? No. It diverges. The series diverges. So that's problem number 27. Next we go to problem 29, and in this case we're given a sigma notation, which I think we could put in our calculator, similar to the way we worked on problem 23. But here, what we have is our R value is equal to 1/4. And with an R value, say since absolute value of R is less than 1, we say series converges. And that's going to be part 1 to our answer here. So the answer, the series converge, yes, series converges. That's our first part. And then if it does, find its sum. Well, the formula we have is sigma equals, we have A sub 1, our first term, divided by 1 minus our common ratio R. In this instance, we're going to have to find out what that first term is. So if we take in this case, J equals 1, we have 3 times 1/4 to the power of 1. That's going to be 3 times 1/4, which equals, what does that equal? 3/4. So that's going to be, so a sub 1 is equal to 3/4. That is our first term. Now, to find this, we're going to say, okay, we'll say 3/4 is our a sub 1 over 1 minus 1/4. Well, that gives us 3/4, and 1 minus 1/4 is 3/4. And 3/4 divided by 3/4, that should be apparent what it is. But if it's not, if we take 3/4 and divide that by 3/4, which is the same as multiplying by the reciprocal of 3/4, which is 4/3, 3/4 times 4/3 is equal to 1. So 1 is our value that this series converges to. And again, we can do this in our calculator. I think I'll just try that. In our calculator, the thing's going to be, we could say, we said J, we'll say K equals 1 to infinity. We're going to use a real large number, 3 times 1/4 to the K. And this time, I think I'm going to use a smaller number, see what we get. Last time I used 100. Let's go here, second row, fourth icon from the right. We have K equals 1. We could use J. We'll say K equals 1. This time, instead of going all the way up to 100, I'm going to say we're going to go up to 10. And we're going to have, what was it here? It was 3 times 1/4. So 3, and remember that's not our initial value, because our initial value was 4/3 once we plugged in 1 for the first J. Okay, we have this. Oh, before we do that, let me go back up here. Okay, open parentheses. I'm going to put in 1/4. And we're going to raise that to the power of K. And we're only going from 1 to 10, so 10 times. We get this improper fraction. If you look at this, we have 1048575 over 1048576. So that's going to be very close. Let's see if the calculator rounds off to. Control Enter. So we get 0.999999. Okay, so that's 999,999 millionths, which is close to 1. If we put a number bigger than 10 here, we would certainly round off to 1. So this really verifies that this is our correct answer. Anyway, I hope this has been helpful. Good luck in completing all the other problems, and I thank you for viewing.